Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And let's see, it looks like we have some questions left over from previous time. So I can maybe start off with these. So there's a question from Keeble92. Can data be sent via light wirelessly? So the answer is yes. One very common way that data is sent via light is in fiber optics. But let's first of all talk about what it means to send data somewhere. So what is data? Data is the video that I'm transmitting here, the audio that I'm transmitting here, the text that you send from someplace to someplace. The first important thing to realize is that all of those things, in the end, are just sequences of ones and zeros. All of those things, whether it's a sequence of characters in a piece of text, an A is represented by some sequence of ones and zeros, 8 ones and zeros. A B is represented by a different sequence of ones and zeros. When we're sending audio, for example, what we're sending is the intensity of sound as it changes with time. That's what as I'm talking, I'm producing different vibrations in the air. That's what turns into the sound wave. That's what we get to transmit. All of these things are ultimately can be thought of as, let's say, sequences of numbers. In the end, sequences of bits, on or off, 1 or 0. So what we have to do when we send data is we've got to do something where we can transmit the knowledge that it's a 1 or it's a 0. So the most common way to do that is through electrical wires, where it's like either there is a voltage, either there are electrons being pushed at that moment in time, or there are not. And that can happen. Are you seeing each bit might take as little as let's say a billionth of a second to be transmitted, and for that billionth of a second, is there a voltage? Is there not a voltage? That's what determines whether there's a 1 or a 0 at that particular position. So when we think about doing this wirelessly, what we're talking about is sending that information through radio, for example, and when we're transmitting things through radio, what's happening is that we have a radio transmitter that's either sending a 1 at a particular time or it's sending a 0 at a particular time, and we have a receiver that's responding to that and that's seeing whether in that particular case electromagnetic wave whether there was a piece of electromagnetic wave at that moment in time or there wasn't. And let's say a billion times a second, it's either it is there or it isn't there, and that's where the 1 or the 0 ends up being transmitted. Now, the most common way to transmit things wirelessly is through traditional wireless, which is radio, which is electromagnetic waves, where what you're doing is you have an antenna which has an electric current that's kind of oscillating in the antenna that's producing this electromagnetic waves that goes through free space. It can go through vacuum, it can go through air, it can go through other materials that don't absorb it. And then it's getting at the other end, the receiver is also, the electromagnetic wave comes in and it causes the electrons to kind of wiggle around in the receiver, and that shows up as an electric current, like a voltage and so on that can be detected. Okay, so that's kind of that approach. Now, can you do the same kind of thing with light? Well, light is just, among other things, another kind of electromagnetic wave. Radio might be an electromagnetic wave where fundamentally the wave is wiggling up and down a billion times a second. Light is more like a wave, electromagnetic wave, where things are wiggling up and down a trillion times a second. Now, how do you, so the idea of how you transmit the ones and zeros, it's like the light is on, the light is off at different times, if you want to make something which transmits, 1100 or something, 11001, it will be the light is on, off, on. Okay, so how does that work? Well, one of the questions is where can you use, how can you transmit things through light? Well, light typically goes in straight lines. So if you want to transmit something, a signal by using, let's say, a laser, you can have a transmitter where the laser is where you're many times a second you're switching laser on or off. There are good ways to do that. There are materials called electro-optic materials where when you put a voltage through the material, it will be able to let light through, and if you don't, it can't, or the other way around. That's how like liquid crystal displays are related to that. I mean, okay, so a little side adventure. What is a liquid crystal display? There are two main kinds of displays that get used for laptops and things these days: liquid crystal displays and light emitting diode displays. I'm going to talk about liquid crystal displays. In liquid crystal, so what is a crystal? A crystal is a solid material where all the atoms are lined up in a very organized way. That's what a crystal is. A liquid crystal is something where you have big long molecules and the positions of the molecules are not lined up like they are in an ordinary crystal. The positions of the molecules aren't lined up, but their directions are lined up. So they're big long molecules. And in a liquid crystal, when the thing is, what you have is a bunch of these molecules where the positions are kind of all over the place, but they're all lined up in one direction. And the reason that's relevant is that when all these molecules line up in one direction, it kind of makes light able only it polarizes light. So what that means is light, normally you can have an electromagnetic wave. If the electromagnetic wave is coming towards you, the electromagnetic wave can be kind of wiggling either up or down or left or right or any combination of those. But if you force the electromagnetic wave to go through this kind of little mesh of molecules, you're forcing it to only be able to wiggle up and down, not to be able to wiggle left and right. And so the way LCD displays work is there's, for example, there's a backlight in your computer display, which is just an ordinary light. And what's happened is the computer display already has one polarizer that is kind of oriented, let's say, in the up-down direction. So light is only getting through from the backlight when the light is polarized, is wiggling up and down this way. Then the liquid crystal is set up so that when the liquid crystal, if there's a voltage put on the liquid crystal, all those molecules line up, it makes this kind of crystalline state. And it makes a crystalline state where it is, let's say, set up to be aligned so that the crystal, so that the sort of the mesh is going the other way. So that means light, if there's a place on your screen where light was coming through from the backlight, it was wiggling up and down, and there wasn't a piece of liquid crystal in front of it that was sort of set up to be aligned, then the light just goes through. It's all good. If, on the other hand, there's a piece of liquid crystal that was set up by a voltage to line up all those molecules, then the light, which was, okay, it's happily wiggling up and down, but now it reaches this thing and it can't wiggle up and down anymore, and so no light goes through. And so then that pixel on your screen is black. So that's kind of how an LCD display works, and you can change whether the molecules are lined up or not very quickly. And that's an example of a way, it's not the most efficient way, there's an even more efficient way to do it, to basically switch on and off a light beam. Okay, so one of the questions then is, how do you get the light beam to go from here to there? If you just have a laser just pointing in free space or whatever, you shine the laser somewhere. If there's anything in the way, you're out of luck. So let's say you wanted to get laser light you wanted to have a light beam that was going to transmit information all the way across the Atlantic. Well, really tough to do, because you'd have to have something which is up in space with a satellite, with lasers, shining from one satellite to another, because if it's on the surface of the Earth, it's curved, and the light will just go in a straight line and won't be able to deal with that. Okay, there's a way around it. It's called fiber optics. And so fiber optics are these little pieces of plastic or glass which have the property that inside a transparent fiber, and you shine a laser in at one end of the transparent fiber, and there are often little toy versions of this. You shine a laser in at one end or light in at one end, and even though the fiber may be bent, the light still comes out the other end of the fiber. How does that work? What's happening is that inside the fiber, the light is bouncing off the sides of the fiber. In other words, it's like having, as far as the light is concerned, it's like the outer part of the fiber acts like a mirror. And so it's like light comes in at one end and it keeps on bouncing from these mirrors down and down and down and down and down until eventually the light comes out at the other end. Now, the really cool thing about optical fibers is that it's been possible to make them so that the light will just keep going in the optical fiber. If there are no imperfections, no sort of glitches in the fiber, I don't know how long it is these days, but hundreds of kilometers at least, hundreds of miles, you can have an optical fiber where you shine a light in at one end and you look at the other end, you can see the light at the other end. And so that's the way that a large part of the infrastructure of the internet is built, is through optical fibers laid in tubes in the ground or under oceans and things, where they are, where the light is being shone in at one end, and it goes, that there can be just a single fiber that can go for 100 miles or more maybe these days, and light comes out at the other end. What happens at the other end? Well, you have to have a repeater where basically you have a receiver of the light, a thing that notices that light's coming in, a photoelectric cell, for example, and then when light comes in, then you, for example, have a laser that that produces a pulse when that light came in. That's a repeater, so that even if the amount of light that came in had gone down a bit, that laser is going to sort of refresh that and produce a nice pulse again. So that's kind of how a lot of communication through light works. In terms of free space communication with light, which I think was the original question, I don't think one sees that terribly much. And I guess that there are just a lot of things that can sort of go wrong when you have when you're just using a laser to communicate with, because it's like anything that isn't transparent, anything that we can't see through, the light of visible light won't be able to go through. With radio waves, it's a bit different. With radio waves, depending on the frequency of the radio waves, you can have the radio waves go through, they go through windows, they go through some kinds of walls, they go through other kinds of things. And also, another thing that happens is because of the frequencies of these things, they can do things like they can bend a little bit when they go around things through diffraction. They can also get reflected off lots of different kinds of things. It's just a little bit easier to get the information, to get the sort of radio waves to propagate around. They act a little bit more like sound waves. I mean, if you're talking at one end of a corridor or something, somebody can hear you around the corner, and that happens because of reflection of the sound, diffraction of the sound, and so on. It's a little bit sort of fuzzier than what happens usually with light, where it's a beam of light and nothing sort of gets outside of that beam. With 5G communications, that's operating on frequencies usually that are somewhere between sort of the most traditional radio frequencies and frequencies, the much higher frequencies of light. It hasn't got quite that far yet, but there's a lot of issues about whether when you use a repeater, this is for communication wirelessly, when you use a repeater, how many, whether things are line of sight, whether you can actually see from the transmitter to the receiver and so on, whether you have to be bounce things off something and so on. Anyway, that's a small response there. Okay, let's see. We have a question here. Oh, that's interesting. Okay, there's a question from Ryan here. How can there be different kinds of twilight, and would you observe the same thing on Mars? Okay, so if you go to Wolfram Alpha, for example, and you say, when is sunset? It's going to tell you, well, the sunset is at this time, but there's also civil twilight, nautical twilight, astronomical twilight. What are these things? So, okay, first question is, what is sunset? Okay, and well, the Earth is rotating. The question is, where you're standing on the Earth, can you see the sun or not? As the Earth rotates, there'll come a moment when you can't see the sun anymore. And what that looks like is, if you look at the sun in the sky, the sun will go down to the horizon, and eventually the sun will go below the horizon. Okay, so first question is, can you predict when that will happen? Well, obviously, you know the rotation of the Earth, you can do all kinds of astronomy and so on, but the precise question of when the sun will go below the horizon is partly a question of, was there a mountain in the way? Was there a tree in the way? How high up were you? Were you at the top of a tall building? Were you down on the ground? All those kinds of questions, and the detailed geometry determines exactly when the sun will seem to set. The other issue is that when light comes to you from the sun, the light doesn't go exactly in a straight line. Light normally goes okay, this is going to be a little bit complicated. So let me just tell a little bit of a story. In Wolfram Alpha, for example, we like to say the sunset is at such and such a time. Okay. Question is, could we say when the sunset is to the second? We can certainly say to the minute when it is, but can we say to the second when it is? Well, it turns out it's very tricky to say to the second when it is. What does it mean for the sun to have set? Well, it probably means that the disk of the sun, which is, the disk of the sun might be about, an angular size, about, the size of your thumb held out at the end of your arm type thing. It's not a point. So there isn't, it's when the sunset might be when the top of the disk of the sun falls below the horizon. Okay, so now the question is, can we predict that precisely, knowing the rotation of the Earth and all those kinds of things? Okay, the answer is it's a little tricky because of the phenomenon of refraction. Same kind of thing that gives you mirages and stuff like that. But what is refraction? So when light, so normally light goes, needless to say, at the speed of light. If it's in a vacuum, light goes exactly at the speed of light. But if light is going through water or glass or some other material, even though the material is transparent and the light eventually gets out the other end, the light doesn't go as quickly in those materials. What's happening? What's happening is, in free space, in a vacuum, an electromagnetic wave is just essentially the photon is just moving. You can think of the light as being made of a bunch of little photons. They're just moving at the speed of light through the vacuum. If they're in a material like glass, what's happening is that's not what's going on. What's going on is that the photon is being absorbed by an atom of glass and then being re-emitted by that atom of glass. So it's kind of like the repeater I was mentioning in fiber optics. It's the atoms in the glass are acting like little repeaters. They're absorbing the photon, then they're re-emitting the photon, absorbing the photon, re-emitting the photon. They're doing that very, very quickly, but it turns out they don't do it instantaneously. It takes a little bit of time between the time when the photon is absorbed and the photon is being re-emitted. And so that means that the light goes slightly slower in glass or water or some other transparent material than it does in a vacuum. And the amount slower that it goes is called the refractive index. And so for water, for example, the refractive index is about 1.33. So that means light is going 33% slower in some sense in water than it is in a vacuum. Or in glass, the refractive index is usually between 1.5 and 1.7, that kind of thing. In a diamond, the refractive index is, I believe, 2.7. So in a diamond, light is going 2.7 times slower than it does in ordinary space, if I remember the refractive index correctly. Different things have different refractive indices. Okay, so what is the significance of the refractive index? Well, that means that one of the most important things is when light, you have a light beam coming in, it hits the surface of water, for example. What happens, and you have to do a little bit of geometry to understand why this happens, but if the light is coming in at a certain angle, the angle when the light goes into the water, the angle that the light goes at will be slightly closer to vertical than it was when the light was outside of the water. So in other words, it's a thing called Snell's law, and there's some trigonometry involved, although you can actually explain it without trigonometry. The sine of the angle divided by the refractive index, basically, when the sine of the angle of incidence, the angle between the vertical and the angle that the actual light is going at. But basically what happens is, as light goes into this material, it starts going slower. And in order for the light not to kind of bunch up at the surface of the material, you can kind of understand by drawing some diagrams that it means the light has to go closer to being vertical than it did when it was coming from the outside. So that's what happens with the light from the sun when it goes through the atmosphere, when it goes through the air around the Earth. The refractive index of air is nothing like water, 1.33. It's more like 1.00, and I don't remember the number. I could probably calculate it. It's let's say it's 1.001. Let's say it's a thousandth of a 1/1000th slower. I don't think that's right. I have to work it out, but it's something roughly like that. That light goes slower in air than it does in a vacuum. So the result of that is, just like when light goes into water, it goes a different angle. Same thing when light comes from the sun, it's going at a slightly different angle when it comes into the atmosphere of the Earth. And so that change in angle means that the precise moment when the sun is going to go below the horizon is depends on just exactly how much the light was bent by refraction in the atmosphere. And this gets even more complicated, because the amount of the refractive index of air depends on the temperature of the air. And so that means that it depends, was it a hot day, was it a cold day, was it hot in the upper part of the atmosphere or not, when the light first started coming in to the atmosphere, and so on. So it's kind of complicated, and that means that there is a correction to to exactly when the sun sets, a few seconds, whatever, that is determined by those kinds of things. That's the first statement. The second statement is, even when the sun has gone below the horizon, there is still, okay, this is where, again, it's a little bit complicated. Okay, let's start off with another basic piece of physics. Okay, why is the sky not black? Light from the sun is coming from a particular direction. That's where the sun is. And light from the sun is coming from the sun to your eye. Okay, why is any of the rest of the sky bright? In space, it wouldn't be. In space, a black sky. There's there's the sun. The sun is in a particular direction. The sun is very bright. Everything else is black. If you go high enough in the Earth's atmosphere, you see the same thing. The one time I flew on the Concorde airplane, it flew at 60,000 feet maybe, and that's high enough that the sky was black in the middle of the day, which was kind of cool. But normally, when the sun is out, so to speak, the sky away from the sun is not black, it's blue. Okay, why is that happening? What's happening is that light from the sun, in space, for example, the only way light from the sun comes to you is it comes straight from the sun to your eye. But in the Earth's atmosphere, what happens is there's light coming from the sun to other places, not going straight towards you, but that it's going and hitting air in the atmosphere, and that air is scattering the light. So what's happening is, just like what I was talking about when light goes through glass or something like this, the light is absorbed by an atom, then re-emitted by the atom. The exact same thing happens in the air. What happens is the light is coming from the sun is here, the light is there's some piece of air over here, some molecule in the air, the light is hitting that molecule, and the molecule doesn't necessarily send the light out only in the direction that the light came in from the sun. It actually sends the light out in all directions, at different rates in different directions relative to where it came in. And so that means that even though the light from the sun is coming only from one direction, when it's scattered from a piece of air somewhere else, the light that came from the sun is scattered in whatever direction and then ends up coming to your eye. And so that's why what you're seeing, and the reason that that the sky is blue is that what's happening is that the blue light is more likely to be scattered than red light. So, light from the sun, white light roughly, it's a mixture of all the different colors, and the different colors correspond to different frequencies of photons and so on. And what happens is blue light is slightly higher frequency, higher energy photons, and they are more likely to be scattered by air molecules than red light. Okay, so what that means is that when the light from the sun that is coming indirectly to you from being scattered is more likely to be blue than red, and that's why the sky looks blue. Now, the converse thing is when you're looking at the sun, then light from that is, if it's red light blue light is more likely to be scattered. That means the light that isn't scattered is preferentially red. And that's why when you look at the sun setting, where the light from the sun is coming through this sort of big column of air, that it is more likely that blue light is scattered away, and so the sun will look reddish as it sets. Okay, but this scattering phenomenon where the sun is where light is scattered in different directions, making the sky blue, that same phenomenon continues to happen even when the sun is below the horizon. So if even that the sun is below the horizon, light from the sun is hitting an air molecule that is not below the horizon for you. And so you can see, and so the light from that air molecule then gets scattered and you see it. And so the reason that the sky doesn't immediately become completely black when the sun sets is there continues to be the scattering phenomenon, much like the reason that the sky is blue during the day. There's light that's being scattered from these from air molecules that still can see the light of the sun, even because they're high up in the atmosphere, and that the light goes from the sun to the air molecule, scattered from the air molecule, comes to you. And that's why it doesn't, that's why the sky doesn't immediately become completely dark. And these different levels of darkness, they usually, I don't know, I think they have different significance in terms of, when, I think civil twilight is, I don't remember how these work, but it's probably when the streetlights are supposed to turn on and things. And maybe astronomical twilight is when, is when the sky is really black. And you can get your telescope out and you're not going to be confused by having light from the sun and so on. And I think, and there are no doubt some sort of ways of characterizing these things about, nautical twilight is when you can't see a ship on the ocean or something. I don't know exactly how these things are defined. Now, there is some more stuff that goes on. There's a thing called zodiacal light. There's some more complicated kinds of sky brightness at night, some more complicated sources of sky brightness. So for example, one of them is there is dust in our solar system, and that dust in our solar system, even when the sun is on the opposite side of the Earth from you, the sun can still illuminate dust that's out in the solar system, in the plane of the ecliptic, in the plane that the Earth rotates in around the sun. There's some dust there, and that dust will be illuminated by the sun. So the Earth might be here, the sun is still illuminating that dust, and that dust is being lit up, and you're basically seeing light scattered from that dust. It's called zodiacal light, and that's one of the things that leads to a certain sky brightness that happens even when the sun is far below the horizon, so to speak. So that's a little bit on how twilight works. Brian is saying sunset over the ocean could be known to the second. Well, that's an interesting question. So I don't know how much it depends on refraction effects. I know that when there was a total solar eclipse that was visible from the US, we went to a lot of effort to try and compute to the second when the eclipse would reach a particular point on the surface. That was hard to do, but I think it depended on the fact that in a solar eclipse, the sun is overhead. The sun is not going through a big column of air. Light from the sun is not going through a big column of air, and I think that has more of an effect. We did manage to nail it to the second. We couldn't get it more accurate than a second. And it started to depend on all sorts of detailed effects there. So let's see. Let's see. Wow, lots of complicated questions here. Okay, there's a question here from Negatronatron. What is the lowest energy anyone has ever produced from electron-positron annihilation, and what range were they dropped into each other? Not sure I can answer that question completely. So reminder about these things: electrons, smallest particles that exist in atoms, carry electric charge. Positrons are the antiparticles of electrons that are exactly the same as electrons, except they have the opposite electric charge. And when an electron-positron, I think I talked about this another time, when an electron-positron collide with each other, they can annihilate each other and produce typically 2 photons, sometimes 3 photons or more photons. So the question being asked is, if you have an electron and a positron and they're just sort of being dropped towards each other, how slowly could they be going? So electron and positron have opposite electric charges, so they'd be pulled together by electrical attraction. But what can happen is that they form a thing called positronium, which is an atom where in an ordinary atom, the nucleus of the atom contains protons and neutrons, but there's and then there are electrons going around that nucleus, so to speak. In positronium, it's kind of a weird thing. You have a positron is the nucleus of this sort of fake atom, and there's an electron going around the positron. So you have these, positronium is this thing that has that can be stable for quite a while. Eventually it will decay into photons as the electron and positron basically interact with each other and annihilate each other. But so when you form positronium, you can effectively, the slowest you can get an electron-positron to be really near each other is in the ground state of positronium. In other words, so what happens is, according to quantum mechanics, in an atom, there are different discrete energy levels. So in other words, an electron, for example, in a hydrogen atom, an electron can either be at a certain energy, or it can be at a higher energy or a higher energy, and there's a whole series of these energy levels. And eventually, when the electron has too much energy, it will escape the hydrogen atom, it will escape the proton that's the nucleus, the hydrogen atom will become ionized, and the electron will just go off separately. With positronium, there's again a sequence of energy levels, just like there is in a hydrogen atom, and the lowest of those energy levels is the energy level at which is the sort of the lowest state that the electron can exist. According to quantum mechanics, it can't have a lower energy in a positronium atom. And I do not know what the lowest energy state in positronium is. Let me think about this for a second. Can I calculate it? Non-trivial real-time quantum electrodynamics computation. I don't think I can do it. Let's see. We need to know. For a hydrogen atom, the energy relative to the free proton and free electron is 13.6 13.6 electron volts. All right. I'm sorry, I can't remember all these numbers. I think I'm not going to be super boring and try and do a real-time quantum electrodynamics computation. And I'm really bad at doing these computations. Like in my head, I really need to be typing on a computer, and that's going to break the flow of all this. So that's as good as I can get there. It's a question from DBA Druid. That's a cool name. How do I become a scientist like you? And how did you make it to create a business out of it? Well, you know, how do you become a scientist? I think in the best case, first you have to be interested in doing it. You know, I think that what do scientists do for a living? What do they actually do? Well, the thing that many scientists like most to do I think most scientists like most to do, is research, figuring out new things. Taking some question about the world, about some scientific question, and figuring out the answer to that question. But often in the practical doing of science, there's a lot of other stuff that goes around that. You have to describe to other people, yes, you should pay for my equipment to go and investigate this question. Yes, I figured out this cool thing. Let me explain it to you. All those kinds of things. There's quite a lot that goes into doing science that isn't just the figuring out the answer to the question. Now, how do you figure out the answer to the question? Different scientists have very different ways of doing that. Some people will, a lot of the time, you're just doing sort of taking steps to use tools to make small progress towards answering the question. And occasionally there's a like, aha, I get it. Now I really understand. And I would say that for me, at least, it's the process of using tools, doing examples, doing little experiments. I always do them on computers rather than physical experiments. That process is the main thing that sort of takes the time in doing science. And that process is what, for me at least, allows me to sort of develop intuition and understand things to the point where occasionally I'll say, aha, I get what's going on. Now I understand how to make some kind of conceptual leap. How do you get to the point of being able to do those kinds of things? I think one very important thing, and probably two important things, maybe more, but two important things are know facts about science and be good at using tools that let you figure out things that haven't been figured out before. Knowing facts about science, if you're going to do science, it's really useful. And people have a habit of learning these microscopic, just very, very, very specific facts about this very specific area. That is not usually the most productive thing to do. I mean, insofar as I've made progress in doing things in science, very, very, very often, it's like there's this thing that comes from over here. There's this thing that I learned about in some completely other context from over here. And the thing that I managed to do is to realize, these are basically the same thing, or they're closely connected. Let's pull these things together, and then we can make progress. And so knowing a lot of stuff about science is really useful. I mean, for me, I have a hard time learning things that I'm not interested in. And so, what tends to happen is I'll learn about some area of science because I'm interested in that specific area, because I'm interested in answering some particular question in that area. And I won't learn about some other area because I'm just not that interested in it. If I try and sort of force feed myself the area that I'm not interested in and read some book about it or something, I usually have a hard time with that. I'm not, one of my personal failings, I'm not particularly good at that. Other people can, usually what I find is if there's an area where, for whatever reason, I really want to make a contribution to that area, I really want to figure something out in that area. Another thing I found is, even an area that I thought, that's completely boring, there's nothing to say about that, as soon as you really dive into it, you realize, actually, there's some pretty interesting questions here. And there really are things which I'd be curious about, and then I'm off and running and exploring that area. But if I try and, without sort of that step, if I'm just like, I should learn about this for the sake of learning about it, I, for example, find that pretty hard to do. In terms of tools, I've spent much of my life building tools to let me and lots of other people do science as efficiently as possible. And that's the whole Wolfram language, Mathematica, Wolfram Alpha story of sort of building this computational language that allows you to sort of make computational the things that you're thinking about and trying to make progress in science. And when I sort of do science, I'm typically doing it, typing things to a Wolfram language notebook and, and getting results from that. And I would say that being knowing those tools well is super, super useful. And it's kind of a superpower for doing science in today's world. I mean, eventually everybody will know that stuff really well. The best scientists, like in most areas, actually, I run into them and it's like, I didn't know turns out they've used Wolfram language for 20 years. And I didn't know you knew that. And then it turns out you look at their code and it's actually quite good. It's, it's quite, they really got it. They understood how to do things. They use it as a tool that lets them really, really make progress. And that's a really worthwhile thing. As I say, for now, it's a superpower. In the future, it won't be. I mean, it's just like at one time, if you knew calculus, that was a superpower in doing certain kinds of mathematical sciences, because only very few people, or fairly few people, knew it. At this point, if you're going to go into various kinds of mathematical sciences, you're going to be fed calculus at some point. You know, everybody's going to learn it. But for right now, you know, learning kind of Wolfram language and so on, and learning it well, not just roughly, but learning it well. And the way to learn it well is to actually try and solve problems with it, things that you're interested in, and figure out how to do those. That's the way to learn it well. And that's a really important and useful skill. Now, in terms of what it takes to sort of do useful things in science, I would say that those two things, know facts, be good at the tools, those are really important. But the thing that is really the determiner typically of how sort of important the science you're going to be able to do will tend to be is usually, do you ask the right questions? That is, so you need the facts, you need the tools, the mechanical ability, so to speak, but you also need to know what's a worthwhile thing to ask about, what's a worthwhile thing to think about. And I would say that the main way that you get to be able to do that is just by doing it. Just by saying, well, you know, I hear about this thing, maybe even some crazy thing I mentioned here might be interesting. It's like, I wonder how that really works. You know, I wonder what the real story with that is. Well, go look up what the story is, then go say, well, I wonder if you could do this or that or the other. Okay, now go figure that out. It's the I wonder whether, et cetera, that leads to kind of coming up with good science. Now, for me, you know, I've tended to notice that you know, the best questions are the most fundamental questions. The best questions are sometimes the most obvious questions. And the mistake not to make is, oh, that's an obvious question, somebody must have answered it. It's amazing how common it is that you'll find a field of science where if you say, what's the most obvious question? Okay, here it is. Okay, has somebody answered it? Maybe yes, maybe no. Maybe it's 50% chance either way. But it's not the case. Just because it was an obvious question, it's been answered. Now, sometimes the obvious question that hasn't been answered is really hard to answer. But often, even the idea that you're going to try and pick away at the fundamental, really obvious question, you can get a lot of mileage by doing that. And if you say, well, let's look at what other people have done in doing this kind of science. Oh, they're working on this little microscopic question over here in this corner, and that must be the kind of thing you can do in the science. That's not true. It's often the case that the big questions, nobody looked at them. And sometimes with new methods that you can bring, with new, you know, tools type superpowers that you have, you can make progress on those questions, even though, you know, it seemed like, oh, those must be really hard because otherwise everybody would have worked on them. It's amazing how rarely people work on the fundamental questions in particular fields. Now, in terms of, you asked also about businesses based on science. You know, I've been lucky enough to find a way to take things that I find intellectually interesting and to map them into things that seem to be useful to the world, so to speak, and that you can make businesses out of. I mean, for me, it's, I kind of backed into 40 years ago now, starting my first company and so on. I was sort of an academic before that, a young academic. I would say that it is a very fortunate case when the things that you find intellectually interesting are close to things which are immediately and directly useful. I mean, I've been working on the fundamental theory of physics recently, and while that is highly interesting, on the face of it, it's not directly related to anything here and now. Now, it's turning out that, to my great surprise, the fundamental theory of physics is leading us to methods that are absolutely relevant to things here and now about distributed computing, generalizations of blockchain, all kinds of other things, which are very much here and now kinds of questions. I wasn't expecting that. I was thinking that it would be something where it was of great intellectual interest, but not really connectable to the here and now. Now, of course, there's a little bit of the, okay, you could do the fundamental theory of physics in a way that was fundamentally unconnectable to the here and now. And the fact is that perhaps because I know a certain amount about distributed computing, I know a certain amount about blockchain, it's like when I see there's this thing where it's, oh my gosh, there is this possible connection, I can actually follow up on that because I have, content knowledge of those areas, and it's not like I don't notice when the thing that is showing up is just like the issues that come up in distributed blockchain, for example. So that's but in terms of the practicality of sort of being a scientist, so to speak, it depends on what stage of life you're at. I would say learning the tools, learning facts, highly important. Ask questions, try and, for me, it's very useful to try and do the kind of thing I'm doing right now, explain stuff to people. I find that a great way to actually understand things myself. And it's a great kind of discipline of knowing that I actually understand something is, can I really explain it to people? So having an opportunity to do that, writing things about the things you do, those kinds of things, those are super worthwhile. I mean, I would mention actual resources, like we have a summer camp for high school students. We have a summer school for grown-ups. We have all kinds of things like this that are at least ways of introducing people to the kind of thinking that I've spent a large part of my time learning how to do. Let's see. There's a question here. Oh gosh, so many questions. Question from Mikhail. Is it possible to do PhD research under my supervision? I've been kind of out of that business for a long time, but we have a mechanism for our physics project, for example, where we have just built this collection of research affiliates and junior research affiliates. The junior research affiliates are people who are students of various kinds, who we are trying to provide some sort of framework and resources and community for those people to work on things. We're not solving the problem right now of, where are you going to get funding for your PhD from? That's a different factored problem. We are providing, however, the mechanism of providing sort of advice and supervision for content kinds of things, and that's something where I'm trying to inject myself in the most useful possible way. I mean, it's kind of something I've learned from running companies for a long time. Is it's not the case that the CEO is the right person to have every discussion about every detail of every topic. That would not be a scalable or useful thing to do. The question is, can you inject yourself at the time when there's a critical decision to be made? In the case of research, can you sort of inject yourself at the moment when there's a key sort of thing to be figured out? And then can you provide sort of resources derived from what you do that work for other places. So we do have a framework for that, and if you're interested in that, please be in touch with us. Let's see. Oh boy, we've got lots of things here. All right, let's try a few things here. All right, I'm going to try from Enrico. Can photons interact? I've heard of light by light scattering, but aren't photons independent quantum activations of electromagnetic waves? Okay, let me try this for a second. So if you have a laser, shine a laser in some direction, you shine a laser in another direction that crosses that first laser beam, the two laser beams won't have any effect on each other, to a very good approximation. Light just passes straight through light. It's unlike material objects, where if you have a jet of gas or something, and you have another jet of gas, and the molecules from one jet of gas will collide with the molecules from another jet of gas, and they'll all get scattered around, and it'll be a different thing. But with light, as far as one knows, in a first approximation, light just goes straight through light. Now, light is if you had a gravity wave, turns out that doesn't happen. Gravity waves interact with each other. So gravitons do interact graviton to graviton, so to speak. But photons don't interact directly photon to photon. So the question then is, do photons have any effect on each other? Well, there's a slightly obscure phenomenon. It's a piece of quantum electrodynamics that's called light by light scattering. And so roughly what happens is this. Boy, this is a little challenging. Okay, So in the world of quantum electrodynamics, I'll say what the official version of this is, and then I'll try and explain it. So light by light scattering is the result of a thing called box diagram, a Feynman diagram. And what it is you have basically two photons come in. They're going to be the two photons that are going to be scattered. The two photons produce an electron-positron pair. They produce an electron and a positron, but these are virtual electron-positron pair, which then annihilate again to produce two other photons. And so in a sense, what's happening in light by light scattering is two photons are coming in, they're turning into an electron-positron pair for a very brief period of time, and then they're turning back into two photons. And the way you perceive that is just, oh, the two photons had some interaction, they scattered. But that's the mechanism underneath by which the scattering occurred. And the thing that so that phenomenon happens, but it happens very rarely. And the higher the energy of the photons, the more likely it is to happen. As the energy of the photons gets to be comparable to the mass of the electron, that's very high energy gamma rays, the chance of this light by light scattering increases dramatically. So for ordinary light, the scattering of light by light for just an ordinary laser beam is infinitesimally small. And roughly, I think if I remember correctly, the amount of the probability of scattering of light by light increases with as the 8th power of the energy of the photons. So it's a very it increases is very small for a long time. When you get to really high energy photons, colliding really high energy photons, and it's possible to do that in particle accelerators, you can essentially have photon-photon interactions. When the energy of the photons is high enough, you can produce all kinds of particles and you can get all kinds of complicated things. But at ordinary energies, like for an ordinary light beam, that's roughly how it works. Let's see. A lot of questions about physics theory. I think it's time for me to do another session about the physics theory. Somebody is commenting, it's hydrogen divided by 2. That is probably my question about the lowest energy of positronium, and I think you are right, because yes, I think you're right. It's just a question of where the center of mass of the thing is. Yep, I think you're right. Let's see. There's a question about postdocs. You should get in touch with us through the Physics Project website. That's the best, or if you're interested in other kinds of computational things, through the company. There's a question here which is more of a general. Okay, there's a couple of questions. Okay, I'm going to try a couple more and then we should wrap up for today. Question from Attore. It says, my supervisor says I should do small projects and publish lots, but person says I'm more inclined to do fewer deeper works. What should you do? I would say if you're a young person just getting started, a large number of small things is better than sort of one very deep thing. Because if you've never done it before, it's really difficult doing a big, deep project. And the trick is to do those comparatively small projects, but to make them, to not make them be, each one should be interesting. Okay, here's a general idea for sort of, okay, the more obvious the question you're answering is, the more likely it is people are going to care about your answer. So if you're working in some area of science and the shortest description you can give of what you're doing is a paragraph long, it's probably the set of people who are going to care is considerably smaller. If, on the other hand, the thing you can that you're talking about is something where you say the question is blah 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 blah, and it's a you know 1 or 2 sentence thing that you're describing, that's likely to be something of more general interest. It's likely to be something where more people are going to care about it. It's a good thing. So I think that, but it doesn't need to be the case that just because it's an obvious question, and you know, it doesn't need to be a question that has to have the biggest, deepest answer. It's like if you can answer that the obvious question, it's already very useful, even though the answer may not be all that deep. And I think it's really difficult to do a big project. I mean, when I started off doing science, I published my first paper when I was maybe 15 years old or something, and it wasn't particularly good, my first one. By the time my second and third papers were significantly better. But they were, you know, modest-sized things, and over time, I got to the point where I liked to make papers that were definitive for whatever they were about. So even though the question might not be this giant, deep question, at least for the particular question, I would just get everything out of that question and just answer it, nail it. And that turns out to be a pretty useful thing to do that people sort of continue caring about decades later. And I think that, you know, doing a really big project, a project that's going to take multiple years, et cetera, et cetera, et cetera, I think very few people can do that successfully without having a fair amount of experience. And the way you get experience is by doing smaller projects. Now, you know, small doesn't mean kind of super specialized and, you know, description is 6 paragraphs long. Small just means it's not doing something like inventing the whole fundamental theory of physics. That's a big, difficult project. It's not doing something like, I don't know, building a giant computational language that's 50 million lines of code and et cetera, et cetera, et cetera. It means it's studying, I don't know, a particular thing I was just studying was something which actually people could have studied anytime in the last 2,000 years. I was studying the empirical meta-mathematics of Euclid, which I'll hopefully be writing about early next week. It's a, you know, that was actually, for me, I thought this was going to be a super easy project. It's only going to take a few days. Actually, it's taken more like a couple of weeks. And turned out to be pretty interesting. But you know, that's a project that I think one could do it. You know, hopefully I've done it decently well, but it probably doesn't need my whole experience base to be able to do that project. It's a comparatively small, well-defined project. But you know, for me, I started off doing much smaller projects, and I gradually, over the course of about a decade, got to the point where I was doing bigger and bigger projects, to the point where I've been doing absurdly large projects. And, you know, having learnt how to do absurdly large projects, you learn a certain rhythm of how to do these things that lets you get through it. I mean, the biggest single project I've done was probably writing my New Kind of Science book, which took about 10 years. And it was just as well, I didn't have to explain to anybody what I was really doing for those 10 years, because, you know, if I was like, had been working at a university or something, and people say, what the heck are you doing? And it's like, well, I'm doing this big project. Really? What, you know, what is it all about? Well, okay, it's, you know, I can describe that one in a sentence, what it's about, you know, exploring the computational universe of simple programs and what the significance of that is. But in more detail, there's just a huge amount to say. So I would say that it's not bad advice to do, you know, doesn't mean do super specialized, but it does mean don't do projects that are going to take, you know, a year or two to do projects that are going to take a month or two to do. There's a question here. That's actually what somebody was commenting. The truth is we still don't have a nice answer, but I'm not sure what that was an answer to. Oh, I see. It's a question about gravity. I should cover that at a different time. There's a comment here. Okay. All right, I'll try one more from Cybot. Is there a hard lesson that you've learnt that impacted you deeply? I don't know. I've had a fairly, I'm happy to say I haven't had a, you know, I've had a life where I've mostly been able to do stuff I wanted to do, and things have worked out decently well, and that's good, and not a lot of trauma, I'm happy to say. Now, to some extent, one makes one's own fate, and part of the reason for that is that I've chosen to do things that are a fairly good match for me, and I've not chosen to do things that are where they're unsuitable for me. I noticed somebody on the live stream commenting that 10 years working on the same project is an amazing thing. It is. That's a good example of a. I was frankly proud of my tenacity in managing to get through a project that took 10 years to do. I mean, in a sense, for example, building Wolfram language, I've been doing that for 33 years now. But that's a project that involves a lot of other people, and it has a lot of different pieces in the rhythm of that project. It's not just one of these, I got to dig in and do the same thing for a long time. Yes, it takes, I would say that my feeling about my personal tenacity, being able to get through a 10-year project, yeah, I've definitely got a certain amount of personal tenacity, and that is necessary to do such a thing. I think the big achievement of that project was to finish it. There are people that, unfortunately, I know who've sort of had, I've got this great big project, and 20 years, 30 years goes by, and you kind of know they're never going to finish it, which is kind of sad. In a sense, my physics project recently was almost an example of that. I had started working on the things that have led to this theory 30 years ago. I stopped again. I kind of stopped about 16 years ago because I wasn't, for various reasons I've described elsewhere, but I almost didn't get to do that project. And actually the very fact that I've now been able in the last year to jump in and do this project, and it's worked out really great, and it's still got lots of distance to go, but it's working out really great. That, frankly, is a tremendous encouragement to me to go do a bunch of other big, difficult projects that I've meant to do for decades. And I've like, am I going to get round to this? Well, the answer is yes, I'm going to do it. A bit more than a year ago, I said, I'm going to try and do this physics project. And I'm like, I'm really going to do it. This is my chance. This is, I've got a couple of young people who are really enthusiastic about working on it. Let's just try and do it. And now I'm encouraged to try and do other such projects. But the question here was a hard lesson that impacted me. I would say that the main lesson is do things that are a good fit for one to do. I mean, occasionally I try and do things that are not particularly good fits. I mean, less so in recent years because I've learned myself better. But an example, back in the early 1980s, I worked hard on a bunch of science about how complexity arises in nature. Worked really well, figured out a lot of really interesting science. I thought, this is a great field for lots of other people to get involved in. Let's create a field, complexity theory, complex systems research, whatever you call it. Let's create this field and let's go make this happen in the world. Well, I think I was pretty good at doing the science. I think I was even pretty good at leading other people if they wanted to do the science. But this phenomenon of kind of organizing the world so that something would happen is not my forte. And what I realized is, I didn't waste a huge amount of time on it, but I wasted a certain amount of time on, going around, figuring out the best university to start a research institute at, to do this kind of stuff. And then I kind of realized this isn't what I want to do. I mean, I can go raise money for other people to do this research, but that's completely not what I'm interested in doing. If I'm going to be involved, the main part of what I'm interested in is being involved in is actually doing the research, not convincing other people to give money to other people to do the research type thing. So that was an example of something where I kind of tried it and I realized this is not for me. This is not what I'm good at. Let me not do this. And that was a useful thing to discover. I mean, I would say that there are other situations that I've been in where for me, everybody is different. For me, I don't mind leading things. I'm happy to lead things, and I don't get sort of I make decisions Some people are like, oh my gosh, what decision should I make? Maybe I'll make the wrong decision and so on. Maybe it's arrogance, maybe it's confidence, maybe it's by this point some experience that, I'm just like, I'll make the decision. Let's just move on, make decisions. Right before this episode today, I was doing some, spend an hour, make a whole bunch of decisions about things. I find that pretty easy. I don't get stressed by it. Other people find that very stressful and are much happier in a situation where it's like, decisions are being made for them, so to speak, and they're being, or they're working with other people to make a consensus decision. Those things drive me crazy. And whenever I'm in those situations, I'm like, oh my gosh, this is not for me. And I get very, just horrible match. And so those are things where, I've learned. For me, I avoid those. For other people, they may be the right thing, and it's So I suppose that's probably one thing. I mean, I think there are other things like for example, you do a big project. Okay, how long is it going to take? Well, hard to know. Very rarely. Okay, so when I get into these projects, like the 10-year project I mentioned, I didn't think it was going to take 10 years. If I'd said at the beginning, this is going to be a 10-year project, it's like, do I really want to do a 10-year project? Do I want to go from age 32 to age 42 doing this project? Difficult decision. Probably no, let's not do it. So, there's a certain amount of optimism that I, for example, will always have going into these projects of, look, I can see my way through this project. How long can it possibly take? And that's a thing where I think that the one example of a project where I don't really think that hard these days about how long is the project going to take. Because if I do, it can't end well. It's like either it's going to take a really, really long time, and then maybe I'm not going to do it, or I'm going to come up with it's going to take 3 months and it takes much longer, and I'm all upset because it didn't take the right amount of time. So I don't tend to think internally too much about that question. I'm just like, is this project a project I want to do? Yes. Okay, great. Let's do it. The physics project that we've done, frankly, it got to where it got to. It's one of the only projects I've ever done, major projects, that worked more quickly than I expected. I think I was pretty efficient in my part of what I was doing there, but it was a project that sort of really exceeded my expectations and was faster than expected. I think, I'm trying to remember, I'm thinking, is there some better response to this question of hard lessons? I don't know. It's a funny thing because I've done a bunch of projects in my life. I think it's fair to say that essentially no major project I've done has ever sort of outright failed. And why is that? Is that because I'm so good at doing these projects, or is that for some other reason? I think there's a different reason. First, I've been fairly, not completely stupid in the projects I picked. But second of all, when the projects are in progress, so to speak, it's like sometimes you realize the direction we're going in, that's not quite the right direction. Let's make a little mid-course correction. And what would have turned into a failure if you just insisted on just walking straight forward in that direction, turned into a success because you just made this small turn in the intermediate stage where to get to a slightly different target because you realize the first target wasn't right. I think, it's this question of look, I mean, there are other pieces that I could expound on about sort of, another thing that I happen to be big on is sort of do the right thing and sort of, act with integrity, even if it's harder to do at the time. Because that's a great way to keep your life simple. Not locally simple. It's often locally much more complicated to do the right thing. But at a global scale, I must say that I have found it in my life watching other people where they don't do that. It's like, oh my God, you get into all this trouble with this and that and the other, and it's all very complicated and so on. And it's just like, just sort of try and do the right thing. Now, sometimes it's not easy to figure out what is the right thing, and you have to kind of zoom out a bit and try and say, what are the principles that you want to follow? You know, how should you treat people? What should you do with this or that? How, you know, it's, but, you know, you zoom out a bit, you realize what the answer is. And even if it's a little bit more effort because you got to explain to somebody why this or that thing that everybody thought was the right thing to do really isn't the right thing to do, and so on. And people are like, oh no, that's wrong. And, you know, there's a lot of flapping about it and so on. You know, at least I've found it's one way of avoiding certain kinds of issues is sort of just try and do the right thing. I would say that the same is true. Look, when you build technology, when you do science, there's somewhat the same kind of thing happens. It's like when you build a piece of technology, do you do it right? Or do you do it in a way that is like, oh, I'm just going to hack something together and it'll be, you know, that's what I'll do. Now, you know, it's complicated because you can say, I'll do it right, but it's going to take me 5 years, by which point the world isn't going to care. It's not going to be the right time, et cetera, et cetera, et cetera. So that's another complicated thing, is that you have to decide, you know, do it right with respect to the thing you're trying to achieve, which might not be sort of the thing you build for the ages, so to speak. Anyway, okay, before I get too much more into personal philosophy kinds of things, although I am happy to talk about those types of things if people find that interesting, but I signed up here for science and technology Q&A rather than personal philosophy, though I'm happy to talk about personal philosophy. I'm not sure that, we should probably wrap up for today. And thank you very much for coming. And, you know, I don't know whether we have a good mechanism for getting feedback about these events, but, you know, I've been doing this for a while. I started doing this when the pandemic started, and I've been having fun. Hopefully people have been finding these interesting, but it's one of these, are there mid-course corrections we should be making? I am seeing quite a lot of questions here that are more advanced science questions. As I say, I think I should do another Q&A about our physics project, where we can talk about more advanced technical kinds of things. And I'm also happy to take suggestions about other things people might find useful or interesting. You know, I find this fun, so hope you like it too, and hope to see you again next time or another time. And yes, we should set up some kind of form to get input for this. Okay, thanks a lot.